So this video is on optimization, and honestly, I'm hoping you've seen a little bit of optimization like skills. I usually show my students Patrick JMT optimization, their first video. He does a pretty good job of explaining what it's all about. So if you just Google search Patrick JMT optimization before watching this, or if you've already seen it, then you should be in great shape. But now I'm going to talk a little bit about more what it's really all about, not just the skills. We're trying to basically find maxes or mins of a word problem. So in this case, we don't have an actual graph to find a max or a min, but everything's being done in exactly the same way. So what makes this tougher is really the geometry, setting up the equations, some things like that. But at the end of the day, we're just trying to find the physical max or the min from a graph. So this is a max here, and this is a min. And it's the same as we've been doing in the other sections. So the optimal solution is what makes you the most money, or uses the least amount of wire, or the least amount of energy, or the most products, whatever you want to say. So let's find maximum volume. Manufacturer wants to define an open top box having a square base, a surface area of 108 square inches. In your textbook, actually, what dimensions will produce a box with maximum volume? So we want to draw a diagram of this, right? It's a box, so it's also an open top box, so just keep that in mind. So I'll just do this thing, and I'll try my best to make a halfway decent looking box here. This is the hard part. Okay, so we have an open top box. And we know that it has a square base. So if the base is square, I'm going to make this x by x for that reason. And I guess I'll make the height y because we love to use the variables x and y. So that's pretty basic. Let's talk about writing some equations. So we do know that it has a surface area of 108. So what are we trying to find the maximum of? Are we trying to find the maximum area, or are we trying to find the maximum volume? We're trying to find the maximum volume. So the primary equation, the thing that we're trying to find is the volume. We want to maximize this. And the way we find volume is we take x times x, and we multiply that by y. So this is the equation we want to maximize. It's x squared y. This is what we're going to want to take the derivative of. We're going to want to set it to equal to 0. We're going to want to see if it's going from increasing to decreasing, the original function, or if the function's going decreasing to increasing. So number line, plus, minus, all that stuff. Secondary equation. Well, they did give us that the surface area is 108. So instead of surface area, I'll put 108 here. And I'm going to ask you how you'd get surface area from this diagram. So back up here. The bottom area is x squared. There is no top. So keep in mind that this is part of the surface area. We need that, but we do not need the top. And then we know that the sides are all exactly the same. And each side, which we have 4 of them, 4 of these, right? We have 4xy. So this is really the surface area of that box. Not too bad. Let's take that and bring it down so we can kind of study that here, okay? Great. So now we have 2 equations, and we know that we want to take the maximum of the one with the volume, because that's the one that we're trying to find the maximum volume, obviously. It's always a good idea to think about the feasible domain. I mean, can x be a negative number? Can x be 0? Can the height of the box be 0? I would say for this domain, really, you want x to be greater than 0, right? And you want y to be greater than 0. It doesn't really make sense otherwise, because you won't really have a box, and you can't really have negative domain or negative dimensions. That's the word. So here's the big one. Use calculus to find the max and the min. Now, they are kind of skipping around a little bit, so let's talk about what that is all about. So we'll bring this guy down here, and we'll bring this guy down here as well, and we'll see if we can get somewhere with it. So we know that this is the equation we want to take the max or the min of. So that's what we're going to need to do calculus on. But we also don't really want to have 2 variables. So how can we get it out of two variables? Well, we could solve for x or we could solve for y. I feel as if solving for y is going to be easier because there's no squared on y, nothing crazy like that. So I'm going to say it's 108 minus x squared all over 4x. So I'm doing a little bit of work there in my head. That's y, and that needs to be plugged in here for y. So let's go ahead and rewrite our volume equation with the one variable of just x now. So we now have the volume, which is what we need to take the derivative of, is x squared times 108 minus x squared over 4x. And I know that x can't equal 0, so there's no harm in canceling out 1x from the top and 1x from the bottom. And another thing that you might find to be very wise would be to perhaps make this just 108x minus x to the third, and just take a 4 out of it, like that. Okay, that's still the volume. And it's much easier to take the derivative of if you just ignore that 4. Now, people make their lives pretty difficult by not just taking this 4 and bringing it down. I mean, it's a constant. And as we take the derivative of v, we get v prime. We can just leave that 4 there and just deal with the variables. So the derivative is 108 minus 3x squared here. So we're getting pretty close. And now we want to figure out where this function is 0 or undefined, the derivative. That's our critical number. That's what we need to put on a number line. When is this 0? So when does 108 equal 3x squared, I guess is our question. When does x squared equal 108 over 3? That's kind of where we are. So that seems pretty ugly. I almost want to check and see if this is correct because the numbers are not nice, and sometimes that's just life. So what we'll do is, I guess, take the square root of both sides, and we'll get some kind of, we'll get something. It just won't be what we were probably hoping for. Probably would have liked some clean numbers there, right? This, by the way, is section 3.6. I'm not sure if I put that at the top of this video, just as I'm flipping in my book here. I've just got a bad feeling about it. 3.6. I guess I didn't put it at all. So let's just make sure that we are aware. This video is 3 point. Hopefully that's a point. Is that it? Oh, there it is. 3.6. Right. Optimization. Okay, not great, but you get the general idea. So just be aware of that. All right, here we go. So figuring out where this is equal to 0 is going to be, oh, there's some great news. 108 divides by 3, doesn't it? It divides by 3 36 times. 36 times 3. 36 times 3. It's 108. So that means that we just need the square root of 36, so x is equal to plus or minus 6, and we don't really want the negative 6, so x is equal to 6 is ideally our dimension. Now, don't just tell me that that's the maximum or the minimum area. Show me. So v prime is here, and 6 is on it. And what we want to do is plug in probably a smaller number, like 1. If we plug in 1, we get a positive here, and plug into v prime. And if we plug in like 10, we'll get 108 minus 300, so we'll get a negative here. So it looks like it's increasing and then decreasing, so x equals 6 is a max. That's good. So let's summarize our answer. We know that in this case, we have the dimensions are 6 by 6 by, this is the x value and the x value, and I think I'm going to use by instead of x. So 6 by 6 by, and then what is y? Well, we know that y is going to be found in this equation, right? So we have 108 equals 36 plus 24y, I think. So when we take the 36 from 108, I suppose we'll have 72, and we'll divide that by 24, so hopefully we'll get y is equal to 3. So the dimensions of this box would be 6 by 6 by 3, and that's our y value. So just to clarify, it's 6 our x value, 6 our x value, and 3 our y value. That's the dimensions of the box. That will give us the biggest or smallest, I guess in this case it's the largest area that we can have. So let's see where we are on the time. Yeah, we're about at 10 minutes, so I think we can talk a little bit more about this problem. Now this problem is going to be a little sneaky, a little tricky. Best way of doing it, probably to like at least visualize it. Let's look at the graph. So the graph looks something like this, and it has a y-intercept of 4, and it's upside down x squared, so it kind of looks something like this, I guess you could say. So this is the graph of that equation. And we want to know which points are closest to the point 0, 2 here, right? So we want to minimize the distance from 0 to 2 to the graph. A couple ways we can do it, but the distance formula might be our best bet. Distance formula. So it's kind of like Pythagorean theorem in a sense. The distance formula is going to be the square root of, and it's going to be x minus the x value squared. So it's going to be x, this is the x value, this is x1, and this is y1, right? So it's going to be x minus x1, which is just x minus 0 squared, plus, and then it's going to be y minus y1. Now, you could look at this and put y minus y1 in now, but I would think it's smarter to just take what y is equal to and then subtract y1. So it's 4 minus x squared, and then subtract y1, and that's our distance formula. So in a way, we had two equations, but now we've really quickly simplified it to one, because I didn't put y into my distance formula. I put what y is equal to. So remember, the distance formula is kind of like, they teach it x2 minus x1 all squared plus y2 minus y1 all squared, and then take the square root of it. It's the Pythagorean theorem. It's the square root of the change in x and the change in y. It's pretty straightforward. This is not going to be too fun to take the derivative of. My thoughts on squaring both sides, I like it sometimes, and sometimes I don't. I think you got to be pretty careful about that, because you're changing things when you're squaring both sides in a way. So you could try to get away with that, or you could chain rule this thing. Simplify the inside. So I'm just trying to give you kind of point you in the direction, and I will just kind of stop here because I don't want to go too far into this. So yeah, we'll take care of the rest of this in the next video. See you there.